Okay, welcome back, everyone. So this is going to be a lesson about linear independence for linear algebra. And everything that we've been doing in the videos so far, we've been still kind of at the beginning of the course. So we're introducing a lot of topics. We have linear combinations, we have span, we have parametric vector form of a solution. And linear independence is another important topic to establish. And then, pretty soon we're going to be able to move on and do things with these. But for right now, a lot of it is establishing definitions and maybe some properties and theorems. Okay, so let's go ahead and get started. Okay, linear independence. So I'm going to start with a question before we get to the definition of linear independence. Question. Let's say we're given vectors v1 through vp in Rn. So you should know that this means we have p vectors, and each one of them has n entries. That's how tall they are. They have n entries. Okay, can we always find scalars C1 through Cp in R so that the following is true. C1 V1 plus C2 V2 plus dot 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 all the way up to Cp Vp equals the zero vector. So if I give you a bunch of vectors, they're all the same size, and then can you find real numbers to make this so that they all add up to zero? The zero vector. Well, the trivial answer, some of you may have noticed, is what if you set these all to zero? That always works. So the answer to the question is yes. Just set them all equal to zero. And then you might say, well, that wasn't a very interesting question. Okay, just set them all equal to zero. Then it doesn't even really matter what those vectors were. How about this as a follow-up question? Are there non-trivial answers? Like, what about besides that? Besides setting them all equal to zero, are there other answers? And for that, it depends. It depends on what the vectors are. And that brings us to this definition. A set of vectors. Now we're talking about a set of vectors, so let's put set brackets around them. v1, v2, up to vp in Rn is said to be, we're going to have two definitions here. They both start out with this. So a set of vectors, p vectors in Rn, is said to be linearly independent. I'm going to underline that. If C1 V1 plus C2 V2 plus dot 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 all the way up to Cp Vp equals zero only has the trivial solution. And in parentheses, the trivial solution is set all of these to zero. So Ci equals That's a ci equals 0 for I equals 1 to p. So some sets of vectors will only have that trivial solution, and we say that that set of vectors is linearly independent. On the other hand, we say the set of vectors is linearly dependent. If there exists, well, what do you think we're going to say? It's going to be if there's some scalars besides just the trivial solution. So if there exist weights C1 dot 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 up to CP, not all 0, such that C1V1 plus dot 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 up to CPVP equals the 0 vector. Now note, when we say that they're not all 0, it's okay for some of them to be 0. Some of them could be 0. A lot of them could be 0. Maybe half of them are 0. Maybe all of them are 0 except for one. You know, there's lots of possibilities. Maybe they're all non-zero. But we just know it's not the trivial case where they are all 0. So I want to show you two examples of sets where we talk about whether they are linearly independent or linearly dependent. And, you know, the title of this lesson was Linear Independence. And that's just when we're talking about this topic overall. We might say we're talking about the topic of linear independence, but a set is independent or dependent. All right, example 1. And I'll talk us through this one. This is the first time we're doing this. Is the set, I mean, if you really wanted to, I think you could do this on your own now based on what we've said, but I don't mind showing us this example and doing it for us. Is this set linearly independent? Now, that's a yes or a no question, but it's kind of implied that, you know, it's yes or no, and show work to justify your answer. Okay? You have to be a little careful in linear algebra classes to check which one is it asking me for, right? I'm not going to try to give you trick questions. I'm not going to try to do that on purpose, but just be extra careful of, is it asking me, is the set linearly independent, or is it asking me, is the set linearly dependent? Okay? Because this is a topic that's going to kind of come up throughout the semester, so just make sure you know which one you're answering, which one is which. All right, here's what we're going to do. Let's try setting up C1. This would be C1V1 plus C2V2. Try setting it equal to 0, and we are going to find out whether or not C1 and C2 exist. I mean, other than just the trivial. You could tell that the trivial solution would work. Set C1 and C2 both equal to 0. That will always work. We want to know if there are non-zero solutions. So what can we do here? This looks like a vector equation. Scalar times vector plus scalar times vector equals 0. How about this? We could simplify the left-hand side to just a single vector. C1 plus 2C2. 2C1 plus C2. That's just a single vector with 2 entries in it. Or you can write it as a system. C1 plus 2C2 equals 0. 2C1 plus C2 equals 0. System of linear equations where the unknowns that we're trying to find are C1 and C2. How can we solve this? Well, we'd probably solve it with the augmented matrix. 1, 2, 2, 1, 0, 0. Let's try to solve the system, see what we get. The unknowns C1 and C2 are what we would find. And maybe, you might look at this and you might say, if you think about it, you could probably skip some of what I wrote. You could probably go from like this line to this augmented matrix. You could probably look at this and say, I know that if I solve this as a system, it's going to have this augmented matrix. Maybe you could even go back a step further and just look at the problem. And you say, hey, as soon as I see this problem, I know that this question is going to correspond to me solving the system with this augmented matrix. So you could probably go straight to this. That would be okay. All right, let's row reduce. I'm going to add negative 2r1 to r2. So we get 1, 2, 0, and then we get 0, negative 3, 0. Now, in a lot of problems that we've had, we've been doing the full Gauss-Jordan elimination where we get something to reduced row echelon form. I think for this one, I'm going to just say we row reduced enough. We got it into row echelon form. Let's just use back substitution on this one. Okay? So back substitution, let me write it here. What does back substitution mean? It means you start with the bottom row and then see what it tells you, and then you work your way up. So row 2 says negative 3c2 equals 0. Okay. From that, I get c2 is 0. And now we see, what does row 1 tell us? c1 plus 2c2 equals 0. Okay, let's try solve for C1. We know what C2 is. C2 is 0. It's gone. So look at that. C1 is 0. We solved the system, and we get only the trivial solution. Okay, I'm going to write on this bottom line the conclusion. There's only the trivial solution. So don't just stop here. Don't just stop here and be like, I'm done with the problem. All right, you didn't answer the question yet. Is the set linearly independent? You did all the work. We did 99% of the work. I sometimes have students that do like everything, but then they don't actually answer the question. And I need you to answer the question to show me that you understand the question. Yes. It's linearly independent. Now we've answered the question. Let's do another one. I think the second one I'm going to ask you to try. So, take as much time as you need to review this one and make sure you understand this one. I've said this before, but a lot of questions in linear algebra really turn into just solving a system. This question, the way it was phrased, this is all it said. It didn't tell us to solve a system. It was just a yes or no question about this concept of linear independence. But we figured out along the way that solving a system would help us answer the question. Okay, so example 2, and I'm going to ask you to try this one, and it's going to be, is the set one one zero 2 2 0 0 0 3 linearly independent? So I'd like you to pause the video, take a few minutes, and try to answer this. Okay, so you should have gotten either a yes or a no, and you should be showing work to justify your answer. And I think this time, to start this one out, I think I'm going to jump straight to the augmented matrix. I think from the first problem, the first problem kind of showed us how this type of question corresponds to solving a linear system. So I can tell that the linear system that I would want to solve would have these columns as the first columns, and then it would have all zeros for the final column because we want the right-hand side to be all zeros. So I did row reduction on this, and we've done row reduction enough now that I think I'm going to maybe skip some of the row reduction scratch work and just kind of jump to the result. I get 1, 2, 0, 0, 0, 0, 3, 0, and then a row of all zeros at the bottom. Now, let's look at each row and each column and see what we can conclude. But I can already tell you that from this row, I can tell that C2 is free. Right? Because normally when we write out a linear system, we think that the first column kind of corresponds to the C1, next one is the C2s, the next one is the C3s, and the final one is the right-hand side. Well, there's no pivot in column 2, so that's going to be a free variable. And there are pivots in row 1 and row 3, so those are going to be basic variables. So from row 2, we get 3C3 equals 0. So C3 equals 0. Now let's look from row 1. We get C1 plus 2C2 equals 0. And C1 could be written as negative 2C2, where C2 is free. Let's try to write the solutions. I mean, I guess we could answer the question now, right? I can tell that there are solutions other than just the trivial solution. I can tell that this means that this is not linearly independent. But I'm going to write out the solution set. Solutions. Remember, we weren't solving for x's this time. We were solving for c's. So we kind of found, let's see, negative 2c2, c2, 0, which if we try to write it in parametric vector form, we would pull the c2 out, and we'd get negative 2, 1, 0. I'm not really going to circle that because that's not really the answer to the question. But the answer to the question, it is not linearly independent. All right, no, it is not linearly independent. It would also be correct to say this set of vectors is linearly dependent. So, you know, it is linearly dependent. It is not linearly independent. So we answered this question, but I think that I want to talk about it a little more. We found other solutions. We found non-zero solutions, non-trivial solutions, right? Because C2 could be something that's non-zero. And then you get what, maybe C2 could be 1. Here, let's write some of this. So further discussion of this result. For example, if C2 equals 1. C2 is free, which means it can be any real number. So if C2 is 1, then C2 times this vector just equals this vector. And we have, let's remember what this represents, okay? C1, C2, C3. That's what those represent. And we do have, remember at the beginning of this video, we said whether it's linearly independent or not, it depends on whether you can do C1 V1 plus C2 V2 plus C3 V3, etc., all the way up to the end of it, and then does it equal the 0 vector? So let's check this. -2 times the first vector plus 1 times the second vector plus 0 times the last vector. You see what I just did here? C1 V1 plus C2 V2 plus C3 V3. Does this equal the 0 vector? You could say that this is a way of checking your work. I'm checking to see, does this work? You could work it all out. I think you might be able to do this in your head. All right, first entry. Let's look at first entries. This would be -2 plus 2 plus 0. Yes. -2 plus 2 equals 0. Yes. How about the middle entry? -2 plus 2 plus 0 equals 0. Yes. How about the final entry? 0 plus 0 plus 0 equals 0. Yes, it checks out. That's just one possible value of C2. C2 could be any real number. But we have a name for this. We call this a linear dependence relation. Okay? It is the full equation written out, the C1 V1 plus C2 V2 plus C3 V3 equals the 0 vector. The full thing written out with weights, which this demonstrates. This demonstrates that the set is linearly dependent. Right? I'm going to show you another one, though. Is that the only linear dependence relation for this set? No, it's not, because we could have a different value of C2. C2 was a free variable. What if I say C2 is 3? Okay. Just want to show you that that gets us another linear dependence relation. In that case, the solution that we got would look like -6, 3, 0. And the linear dependence relation that we write would have -6 times the first vector plus 3 times the next vector plus 0 times third one. Does this equal all zeros? I'll let you check that out, but yes, it does equal the 0 vector. I'm going to put a check mark next to it. So this is another, this is another linear dependence relation. So same set of vectors can have more than one linear dependence relation. We could keep going with this. Remember, C2 is a free variable. You could pick your favorite real number for C2. Let C2 equal pi. Let C2 equal the square root of 2. Let it equal 17. Whatever you want, you will get another linear dependence relation. So there's infinitely many of them. And by the way, the reason let me be clear. The reason why there's infinitely many of them is because we had a free variable. Okay. All right. Let's talk about, there's a connection here between what we're talking about now and what we talked about in the previous lesson. So let's move this up a little bit. So I think now you know how to answer those types of questions. If I give you a set of vectors and ask you, is it linearly independent? Show work to explain why. I think you can do that. Connection to previous video lesson, the one right before this. We said the homogeneous system AX equals 0 always has at least the trivial solution. Certainly seems like there's some connection between that sentence and what we're talking about today. So I'm going to put in quotation marks because I'm going to kind of put this as like a sentence I'm saying, or a question I'm asking. Is there a non-trivial solution to AX equals 0, question mark, is the same as? I want to say that that question is equivalent to the question, are the columns of A linearly dependent? Think about that for a minute. I'm not asking you a question right now. I'm just asking you to try to absorb this. So there's this connection between there being non-trivial solutions to a homogeneous system and the columns of the coefficient matrix being linearly dependent. If the answer to one of these is yes, then the answer to both of these is yes. If the answer to one of these is no, then the answer to both of these is no. Of course, it depends on what matrix A is given. I'll show you an example. Let's do a 2x2 example. So consider AX equals 0 vector where A is 1, 2, 3, 4, the 2x2 matrix. So I'll walk us through this. Let's see what happens when we try to when we try to work with this system. So AX would be the 1, 2, 3, 4 times this. In the previous video, we saw how to multiply a matrix times a vector, right? You take the first entry of the vector times the first column of the matrix, plus the next entry of the vector times the next column of the matrix. And we are asking, we want this to be 0. Okay. Let's talk about this. The unknowns are called x1 and x2 because I'm kind of phrasing this as AX equals 0, which is kind of like what we did in the previous video. But today we've been having like a C1 and a C2. It's just a different labeling. They're just labeled differently. That's okay. I'm going to say so AX equals 0 has a non-trivial solution if and only if the columns of A are linearly dependent. Dependent. Because that would mean there is a non-trivial solution to this. And let's find out. Let's find out. You know, we're asking both, we're asking, does this have a non-trivial solution? And we're also asking, are these columns linearly dependent? So we'll set up the augmented matrix 1, 2, 0, 3, 4, 0, and let's work with this. I'm going to add negative R3 to R1. I get 1. Hold on. Why am I saying R3? Hold on. Scratch that. That doesn't make sense. What row am I talking about here? I think I was looking at the wrong part of my page. What row reduction step would make sense here? If we were in person, I would ask you, and let's say I want to get rid of this 3. I saw a 3, and I was just thinking about that. Let's add negative 3 R1 to R2. That makes sense. Multiple of row 1 is getting added to row 2. Row 1 is staying the same. Row 2 is going to get a 0 there. That's what I wanted. The 4 is going to get a negative 6 added to it and become negative 2, and the 0 is still 0. I'm going to row reduce further. I can see that this row reduces to 1, 0, 0, 0, 1, 0. Okay. Row 2 says x2 equals 0. Row 1 says x1 equals 0. So we get the trivial solution only. There were no free variables. There's no other solutions. So ax equals 0 only has the trivial solution. The set of its columns, its column vectors, I'll say is a linearly independent set. Okay. Independent. So we only got the trivial solution. When we write this, it's a set of these two vectors. So I said this is a linearly independent set. Sometimes we'll casually talk about this, be a little bit more informal, and we might say something like, those vectors are linearly independent. If I said those vectors are linearly independent, you know that what I really mean is the set containing those vectors is a linearly independent set. Okay? So what we'd like to do next is we'd like to come up with some shortcuts and some rules and some theorems that help us tell whether or not a set is linearly independent, especially because there seems to be this connection between a set being linearly dependent or independent and a system having solutions or not. So it would be nice to be able to tell if things are linearly independent, maybe with some shortcuts. It seems to me like the smaller the set, the easier it should be to answer. So we're going to start with sets of one vector. A set of one vector. Fact. I don't think that this is called a theorem. I think this is something that kind of follows from the definition of linearly independent. A set of one vector. Let's just call it V. I mean, we don't really need to call it V1. If there's only one of them, we can just call it V. A set of one vector is linearly independent if and only if V is not the zero vector. All right, so you'd be setting up like C1V and asking yourself, is there a non-trivial weight C1? Works out as long as the vector is not the zero vector. Do we need to show examples of this? You know, example, let's make a set of one vector. 1, 2, 3. This is linearly independent. How do I know it's linearly independent? Because it's only one vector and it's not the zero vector. Boom, we're done. We're using this fact as a shortcut. And that does kind of follow from the definition from earlier. Okay, so that's about all we can say for sets of one vector. I mean, sets of one vector probably don't show up very often. It starts to get interesting once you get to sets of two vectors. Now, if I gave you a set of two vectors and I asked you, is it linearly independent or not? I know one way you could do it. We did this already, right? We had a set. It had two vectors. We asked, is it linearly independent? And we answered it by solving a system. It turned out that we only got the trivial solution. So you could always do this, right? And any theorem or fact that I'm about to say would be potentially a shortcut that lets us skip some of this. But this would still work, right? So if you have a set of two vectors, we have a theorem. A set of two vectors, let's call them V1, V2, is linearly dependent. So remember which one that means. Remember which one that is. It's linearly dependent if and only if one vector is a multiple of the other. And we're going to prove this. We're going to prove this. So the recommended textbook that I'm referencing, I think that book just calls this a fact. I think it doesn't call it a theorem. It calls it a fact, and the book doesn't prove this statement. But I looked at it as I was going through, and I was thinking, I think we should really write a proof to justify this. This is something we could use as a shortcut. Like even that problem that I showed you earlier, two vectors. Maybe you could look at it and just tell by looking at it, is one of those vectors a multiple of the other? It would be a really nice shortcut for us to have. So I'd like us to prove this. This is an if and only if statement. Now, you know from previous course that you took on how to write proofs, how to prove an if and only if statement, you need to prove both directions. So it's kind of like two proofs in one. We need to show that the first thing implies the second, and that the second thing implies the first. So I think what I'm going to do is I'm going to do half of the proof, and then I'm going to ask you to try the other half. I am going to work on this direction of the proof, the forward direction. So I'm going to say, let's make 2 paragraphs for this proof. 1 paragraph for this direction, and then you'll work on the paragraph for the other one. Suppose V1, V2 is linearly dependent. So my job right now in this paragraph is I am going to prove that one of them must be a multiple of the other. That's kind of tricky because we're just keeping them as general vectors. We don't know what entries they have. I could use the definition of linearly dependent. All right, how about this? We're going to maybe break this into cases. I'm going to say first, if V1 equals the 0 vector, or V2 equals the 0 vector, then one vector is a multiple of the other. Can you see that? If one of them or the other is a 0 vector, then yeah, definitely one is a multiple of the other. So, for the remainder of this, let's suppose that we have the other case. We have this is not 0 and this is not 0. So we already took care of the case where if one or both of them are 0, then we're done. So let's now say they're both non-zero. We have C1V1 plus C2V2 equals 0, where at least one of C1 and C2 is non-zero. How do I know that we have that? Why was I allowed to write that line? I'm saying this is true. We have C1V1 plus C2V. The reason why I'm able to say this is because the first line of my proof said we suppose that they're linearly dependent. So now I'm using that. They're linearly dependent, so we do have this where at least one of these is non-zero. Okay? So I'm going to rearrange this. C1V1 is equal to negative C2V2. Again, where at least one of them is non-zero. I don't know which one is non-zero. It's C1 or C2, but at least one of them has to be. So how about this? If C1 is non-zero, then we can divide by it and say V1 is negative C2 over C1 V2. The other possibility is C2 might be the non-zero vector. In that case, we could say that V2, divide both sides by negative C2, and you get negative C1 over C2 V1. Do you see what I've done here? In either case, one vector is a multiple of the other. We wrote it that way. V1 is a constant times V2, or V2 is a constant times V1. So we used the fact that the set was linearly dependent to say ultimately V1 is either V1's a multiple of V2 or V2's a multiple of V1. That's exactly what we were trying to prove. So that's the end of this part of the proof. So I'd like you to try proving the other direction. So it's an if and only if proof, so you need to now go in the other direction. So I'm going to say it'll be, about the same amount of work. It'll take about 1 paragraph. So this is a good place for you to pause and give this a try. Okay, so I think hopefully what you're seeing is linear algebra. You know, we have a course that shows you, an introduction to proofs, and that's a prerequisite for linear algebra. It's because we do proofs like this. And hopefully what you're seeing is that linear algebra is kind of a mix of computation and proof writing. So we are going to be, you are going to be asked to write some proofs, and then some problems will just be straight computing. Evaluate something, solve something. Anyway, we could start by, if you're not sure what to do, start with what you know. What are you trying to show? What do you know, and what are you trying to show? We know that we could do, suppose one of these vectors is a multiple of the other. Okay? I always say that in proof writing, if you're stuck, don't just sit there staring at the page and not writing a single thing. Write what you know. You know that for this direction of the proof, you're trying to assume this side, one vector is a multiple of the other, and then you're trying to prove that the set is linearly dependent. You could even write a sentence here if you want. You could say, we want to show that this set is linearly dependent. This means we want to show, right, C1, V1. Like, you can sometimes get the ball rolling by just writing what you know. I'm gonna skip some of that stuff I just said out loud. I'm gonna look at this and say, what can we infer from this? One of them's a multiple of the other. Do we want to break it into cases? Maybe we could do that. We could say, oh, maybe, V1 is a multiple of V2, or V2 is a multiple of V1. Here's this. Here's what I'm going to do. I'm going to say without loss of generality. All right, so hopefully you know what that phrase means from a previous course, but basically it means we could just take one of them, write it as a multiple of the other. I'm going to say V1 equals this constant times V2. If I wanted to do the other one, V2 equals B times V1, it's not really going to change anything. It's the same thing. So we say without loss of generality, let's just say V1 is the multiple of V2. All right, now, what do we know about this number A? We don't really know too much about it, right? Could A be 0? Does that count as a multiple? How about this? If A equals 0, then C1 V1 plus C2 V2 equals the 0 vector. That results from the non-trivial weights C1 equals 1, C2 equals 0. Now, I kind of got this by observation. Here's the idea. If A is 0, then V2, we don't know what V2 is, but V1 is the 0 vector, right? Because it's 0 times something. So V1 is the 0 vector. Now, all we would have to do to get a linear dependence relation is maybe do a 1 here and a 0 here, and you would have 1 times the 0 vector plus 0 V2. And that would work. That checks out. So if A is 0, we get what we wanted. What if A is not 0? That's what we need to consider next. So you could, if you want, depending on how you prefer to write proofs, you could label this. You could say like case 1 if A equals 0, case 2 if A is not equal to 0. That's kind of just a matter of style preference. I chose just to write it. Suppose A is not equal to 0. I chose to write it without saying case 1, case 2. But it is kind of like two cases. The case where A is 0, the case where A is not 0. All right, you know by now that there's some flexibility when you're writing proofs to kind of write something in your own style. But make sure you're using complete sentences. Make sure that you are ending sentences with punctuation, doing all the proper things that you should have learned in a proof class. Okay, that is still important. Sentences start with an uppercase letter, proper grammar, you end with punctuation, all of that. All right, suppose A is not 0. We want to find C1 and C2 so that C1v1 plus C2v2 equals the 0 vector. What we're going to do is take this line that we're trying to show and combine it with this line that we said earlier. We said V1 is A times V2, okay? So we have, it's a good place to say we have, C1V1 plus C2V2 is really equal to C1AV2 plus C2V2. Is everybody okay with that? V1 was a multiple of V2, so just do that instead of V1. Now, because of properties we have about scalars times vectors, we could pull out C1A plus C2 times V2, period. We started with this left-hand side. We're trying to show that this thing equals 0. Or I guess I should say we're trying to show that there are weights C1 and C2 so that this will equal 0. So we can decide what C1 and C2 are. So let C1 equal 1. I'm looking at this, I'm trying to ask myself, what should I make C1 and what should I make C2 to guarantee that this thing equals the 0 vector? I don't want them both to be zeros. That would be the trivial solution. But can I find a non-trivial C1 and C2 that makes this whole thing 0? And here's what I found. Let C1 equal 1 and let C2 equal negative A. Do you see that that's going to work? C1 is going to be 1, so we're going to have A here. C2 is going to be negative A. Ah, that's going to work. This yields a linear dependence relation. Because then, let's write it out. Just to be, just to be clear, you might be able to get away with skipping this, but I think this is going to be a nice way of wrapping it up. Because then this equals this equals this equals the 0 vector. That's what we were trying to show. So that's the end of the proof. I'm going to put a square there. What did we show in this second part? We supposed that one of them is a multiple of the other. We suppose one of them is a multiple of the other, and we conclude that the set is linearly dependent by demonstrating a C1 and a C2 that gives us a linear dependence relation. There might be a different C1 and C2 that you could choose. Just make sure they're not both 0. Maybe the C1 and C2 that I chose, maybe instead you decide to do -1 and positive A. I think that would work. -1 and positive A would also be a linear dependence relation, and there might be other ones too. All right, so that was a little bit tricky. You know, sometimes, just like with a proof class, you know, sometimes you have to work with it for a while, do a little scratch work off to the side if you think it'll help. But in this class, a lot of times you can also refer back to definitions, like what's the definition of linearly dependent? And what does it mean to be a multiple of each other? So where are we at so far? So far, we had a brief discussion about sets of one vector, and we have a shortcut for telling if a set of one vector is linearly independent or not. Then we just had a theorem that we proved, which, if you go back to the statement of the theorem, I'm going to show you the statement of the theorem again. We proved it, but now let's not forget what the theorem was. We can use this from now on as a shortcut. If I give you a set of two vectors and I ask you, is this set linearly independent or linearly dependent? You could solve it the way we did earlier today, where we're solving a system, and you could get your answer that way. There's nothing wrong with that. But sometimes you can just look at the two vectors, and you can tell if one vector is a multiple of the other. And from that, you can reach your conclusion. And you can say, by a theorem that we proved in class, because one of these vectors is a multiple of the other, right? You get your answer that way. So that's really nice. Here, I'll show you a couple of quick examples. I'm not going to write a lot of words here. These are just going to be quick examples. This set is linearly dependent. Can you see that very quickly? We could write more explanation, right? But let's just say this set is linearly dependent because one of the vectors is a multiple of the other. You agree with that? So one of those is definitely a multiple of the other. That saves us some work. We didn't have to like set up a system and solve it. Here's another quick example. Remember, this theorem is just for when you have a set of two vectors. So we're not going to use this for sets of three vectors or anything like that. All right. How about this set of two vectors? How about you see this and the question is this set linearly independent or is this set linearly dependent? Well, you look at these two vectors and you ask yourself, is one of them a multiple of the other? Is there like scalar I could put in front to make one of these a multiple of the other? And I would say no, there's no way that one of these is a multiple of the other. Right? I can't imagine saying that this equals a real number times this. It's not going to work because that 3 and that 0, we're not going to get those to match up, and that 0 and that 5, they don't match up. Not like the 1 and the 10 and the 2 and the 20. Those matched up really nicely. But here, I'm going to conclude that this set is linearly independent because it's a set of two vectors and they are not multiples of each other. So that theorem is a nice shortcut. So we have shortcuts when the set only has one vector and shortcuts when the set has only two vectors. Now, I've been using the word shortcut. Don't forget that you can always test for linear dependence by solving a system like we did in examples 1 and 2 earlier. Okay? So if I gave you a set of two vectors and you couldn't, I don't know, maybe if you thought it was hard to tell if one is a multiple of the other, you can always do it like we did in example 1 and example 2. Now, one of those examples we did earlier, I guess it was example 2, had 3 vectors. It didn't have 2 vectors, it had 3 vectors. So you could do it the way we did earlier. But we also have some theorems that might help with sets that have 3 vectors or 4 vectors. So we're going to go through a few theorems here. This is going to be theorem 7. It says a set of 2 or more vectors, S equals V1 through Vp, is linearly dependent if, so far, we should be looking at this sentence so far and we should be getting excited. We should say, okay, yeah, I like where this is headed. This seems like it's going to give us a shortcut. It gets better. You want to see how it gets even better? If and only if. Okay, now things are getting really good. Now we're feeling like, yeah, we're getting a nice shortcut out of this. Okay, if and only if at least one of the vectors in S is a linear combination of the others. Well, it is a shortcut. It might not be quite as easy of a shortcut as those other things we said earlier. This is going to be a theorem that you use in some problems. This is not really going to be something you want to use for every problem. Now, let me say a couple of things. This is theorem 7, and I think earlier today we had a theorem that did not have a number attached to it. And in the previous video, we might have had some theorems. I'm referring to the recommended textbook, and when I say things like theorem 7, that's what it's called in the book. We're not going to cover every single theorem. So if it seems like we skipped some numbers, that's okay. I also want to say that we're not going to prove this one right now. The proof is in the book, and you could refer to that. We just proved something a few minutes ago, and I think we're also going to prove theorem 8 pretty soon. So we'll do some proofs and skip some proofs. What I would rather do instead of proving this is I'd like to show you an example of using it. So let's say we're given a set that has 3 vectors. And I'm not going to write it all out, but let's just say the question is this set linearly independent or dependent? So here's a question. Is one of the vectors a linear combination of the others? Can we tell? Is one of these a linear combination of the others? Sometimes it might be easy to tell. Sometimes it might not be easy. I'm going to say yes. Because I noticed that I could write the linear combination 1 times this plus 1 times this, and it equals the other vector. Since 3, 3 is a linear combination, of the other vectors, as shown above. This is me trying to justify my work, justify my answer, explain why my answer is what it is. The set is linearly, which word is going to go here? Linearly, think about that. Dependent. Okay? So that is an example of how to use Theorem 7 as a shortcut. I did not have to set up a system and solve it, because in this case, the vectors were simple enough that I was able to look at them for a minute or so. And after looking at them for a minute, I was able to spot the linear combination. I was able to say, wait a second, that one looks like the other two added together. So if you can spot a linear combination like that, then you can use this as a shortcut and explain what you did. You know, since this is a linear combination of the other vectors, as shown here, the set is linearly dependent. End of the story. You don't have to necessarily solve a system. So that's pretty cool. That's one shortcut that might help us. And that says a set of 2 or more vectors. I kind of feel like the more vectors you have, like if you had 5 or 6 or 7 vectors, at that point, it gets difficult to notice the linear combination. That's how I feel. I think the more vectors you have, the harder it is to identify that there's a linear combination happening or not. But when there's only 3, sometimes you can do this. We have, I think, 2 more theorems that are also going to be shortcuts. And these other 2 theorems are also focused on these cases where you've got, you know, a large number of vectors. So sometimes you could use Theorem 7, but you don't always use that. Theorem 8. This one we're going to prove. If a set contains more vectors than there are entries in each vector, then the set is linearly... Which one do you think I'm going to say here? Which word do you think we're going to finish this with? Think about that for a second. Linearly dependent. All right. So let's prove this. Let's prove this. This is saying that if you have a lot of vectors, so for example, it doesn't even have to be like a gigantic set. What if you have 3 vectors, but there are only 2 entries in each vector? By Theorem 8, that means the set is linearly dependent. I'll show you an example of this, okay? You ready? Example? Example is right here above us, this one up here. We could have used Theorem 7 or Theorem 8 for this. So this set contains more vectors than there are entries in each vector, because there are 3 vectors, but there's only 2 entries. So we could have just looked at this and said, by Theorem 8, this set must be linearly dependent. It has more vectors than there are entries in each vector. That's a pretty cool shortcut. That means that there are some problems, not all problems, but some problems that you'll be able to just look at very quickly, and say that set has to be linearly dependent, because look at how many vectors there are, and look at the size of them. I want to warn you that this one is not an if and only if statement. This is just if, then. Let's try to prove this. And I guess the fact that it's not if and only if means we only have to prove one thing. Okay, so I'm going to walk us through this proof. I might kind of ask you to think about some parts of it, but let's start. How would we do this? we need to start by saying, let's suppose we have a set of vectors. Furthermore, let's go ahead and assume that the set contains more vectors than there are entries. We have p vectors. Each of the p vectors looks like it has n entries. So let's suppose that p is greater than n. That's good. I'm going to do some scratch work off to the side. Scratch work. Because where we're at right here, I'm imagining a set. It could be 3 vectors with 2 entries. It could actually be something bigger than this, but let's say, we don't really want to assume certain numbers here. So let's just say we're dealing with something of this kind of shape and size or bigger. Let's remember, what are we trying to show? We're trying to show that this set is linearly dependent. Let's work with the scratch work side of things. Could we show that this set is linearly dependent? I guess what we would do is we would have C1 V1 plus C2 V2 plus C3 V3. We're trying to show linear dependence. All right, we want to find something other than the non-trivial solution. I'm sorry, we want to find something other than the trivial solution. How would we do this on the scratch work side of things? How would we look for a non-trivial solution? Well, we would set up a system. Augmented matrix would look like, this is scratch work, so it doesn't have to be perfect, but this would be the augmented matrix we're trying to solve. Looking at this augmented matrix, this is not the proof, by the way. Like, this stuff in blue off to the side is labeled as scratch work. We're going to get back to the proof and write it properly. I'm just trying to figure out what our strategy is. We want to explain why there must be non-trivial solutions. So I'd like you to think about this for a minute. I'm still going to help with the proof. But think about this. Can you figure out, maybe based on this scratch work, why does it look like there must be non-trivial solutions? Okay, so I'm writing a lot of scratch work off to the side here, but I'd like you to think about, does this look like it would have free variables? Do you think that there would be at least one free variable for an augmented matrix of this size? Well, I mean, how many pivots could there possibly be? In my little picture here, maybe the first row has a pivot, maybe the second row has a pivot. But there has to be at least one free variable, right? You could look at a fact from the previous video lesson, just the previous lesson, and it said, I'm kind of going to, I guess this scratch work is turning into like a complete informal version of the proof, and then we'll write like the more formal version of it here. Sometimes that helps. But we had a fact that said that this homogeneous system has non-trivial solutions. If and only if, I'm going to abbreviate if and only if, there is at least one free variable when solving. So off to the side, I think we have got everything we need. We've got all the major pieces of this puzzle to write this proof. I do think that this has to have a free variable. And then because of that, I think there has to be a non-trivial solution. And then because there's a non-trivial solution, the set has to be linearly dependent. Let's think about how we would write this up more formally as a proof. I don't really want to write these like vectors that look like they are assuming things are a certain size. This looks like I was assuming that there's only 2 entries and that there's 3 vectors. But in general, this augmented matrix seems important. What I'm going to do is I'm going to let A equal this matrix. Seems okay, right? Then the homogeneous equation AX equals 0. What do you think I'm going to say next? Something about the size of it. I'm going to say that it corresponds to a system of n equations with p variables. Since p is greater than n, we said that up here, we knew that was going to be important. Since p is greater than n, there is at least one free variable. There could be more, but there's at least one. Therefore, AX equals 0 has a non-trivial solution and I'll remind you that earlier I said, well, I don't know if I necessarily want to bring the page in front. Let's go ahead and do it. Real quick, look at where we're at. Therefore, AX equals 0 has a non-trivial solution. Remember this thing from earlier? Is there a non-trivial solution to AX equals 0 is the same as, are the columns of A linearly dependent? Good. Therefore, non-trivial solution and the columns of A are linearly dependent. End of proof. Cool, that was a cool little proof. We kind of did a scratchwork version of the proof, and then we did the actual version of the proof. So, let's look at the theorem again. So anytime you have a set with more vectors than entries, you can use that as a very quick shortcut. It means that you probably won't get a lot of those problems because they're kind of the quickest ones for you to answer. But you might see some of them, and whenever you see one of those, you should be happy. You should be like, oh, that's a Theorem 8 problem. And theorem 8 problems I can answer really quickly and just write like maybe one sentence to justify. You don't necessarily have to call it theorem 8. You could say that if you want. You could say by theorem 8, blah, blah, blah. But we're going to have so many theorems that I don't expect you to like memorize which one was theorem 7 and which one was theorem 8. So you could say something like, by a theorem proved in class, since this set has more vectors than entries, it is linearly dependent. Something like that. But remember, this one's not if and only if. You can't assume the other direction. Got one more theorem for us on this list of theorems about linear independence. And I hope that you're seeing that each one of these theorems is somewhat of a shortcut for answering the question of whether a set is linearly dependent. This one is a little bit simpler. It says if a set V1 through VP, subset of Rn. Notice that this has P vectors with n entries. It's not assuming a certain size, so it doesn't say that it's 2 vectors or 3 vectors. It's just more general than that. If a set contains the 0 vector, then the set is linearly dependent. Ooh, that's a nice quick shortcut. If I gave you a set and you saw that one of the vectors was the 0 vector, you automatically know that that set is linearly dependent without having to solve a system. You don't even necessarily have to think about theorem 8 or theorem 7. You say, oh, it has 0 vector. It's linearly dependent. I'm going to show you a proof of this. Okay? I'll show you this proof. Unless you really want to try it on your own. Maybe you could think about it. So up to you if you want to pause the video and try this. There are P vectors, okay? And at least one of them is the 0 vector. Do we want to write a case for each? Like case 1, suppose V1 is the 0 vector. Case 2, suppose V2 is the 0 vector. Case 3, and then go all the way up to case P. That would be kind of messy. This is a good example of where you could say, without loss of generality. Without loss of generality, suppose V1 is the 0 vector. Because if it's not V1, if it turns out that it's V2 or whatever, you can just relabel the vectors and move them around in this little set. Sets, in a set, it doesn't matter what order things are in. So if at least one of these is the 0 vector, we can just suppose that it's the first vector, whichever one is labeled V1. Okay? Otherwise, relabel the vectors so that V1 is the 0 vector. All right, then we have, I'm going to show you that this set is linearly dependent. And in order to show you that it's linearly dependent, all I have to do is show you a linear dependence relation. How about this? Is this a linear dependence relation? Well, the whole thing would add up to it would all add up to 0. It would all add up to 0, and the weights are not all 0. So I can just say, which is a linear dependence relation. That's what we're trying to show, linear dependence. We showed a linear dependence relation. So end of story, end of proof. That was like a two-sentence proof, if you write it that way. Pretty cool. Pretty cool. All right, so this lesson has turned out to be kind of a longer one. You know, this is the lesson on linear independence, and we started by talking about what it means to be linearly dependent or linearly independent. We did a couple of examples where we answered the question of linear independence basically by solving a system. And then we've spent a bunch of time coming up with facts and theorems that could provide shortcuts that let us skip the system solving and quickly tell whether certain sets are linearly dependent or not. That doesn't mean that these shortcuts are always going to work. You still might have to fall back to the original method of solving a system manually. So what I'd like to do right now is I'd like to give you a few questions and have you spend a few minutes trying them. I'm going to write 4 of them, and this is definitely something that after I write all 4, I would like you to pause the video and try these. Some of these might use shortcuts, some of them might not. I guess when there's a shortcut problem, it's still up to you whether you use the shortcut or not. Some of them might have more than one shortcut. Anyway, if we were in class, I would probably give you these and then give you probably about 10 minutes to try to work on these. It's going to be a part A, B, C, D. So wait until I've written all 4 of them. Three zero 5 0 3 0. That's our first set. Part B, the set containing the vector 1 0, the vector 0 1, and the vector 1 1. Part C, the set containing the vector 1 negative 2, and the vector negative 1/2 1. And part D, the set containing the vector 5 negative 1 0, the vector 8 negative 2 2, and the vector 0 1 8. All right, so I'd like you to pause the video, spend some time working on these, and see what you can come up with. Okay, so I just stepped away for a little bit, and we are back to talk about these solutions. Remember, there could be more than one way to solve some of these. So I'm going to try to go through these where I think some of them I could just answer just off to the side. They don't really need much space. Part A, I'm going to say there are 2 vectors. So I'm thinking about that shortcut for sets containing only 2 vectors. I'm going to say neither is a multiple of the other. So the set is linearly independent. And that's good. That's really all you have to say for part A. I mean, you could say a little bit more, but you don't really have to do a great deal more than that. All right, I think we can tell by observation that 0 3 0 is not going to, like, that neither of these are going to be a multiple of the other because of where the zeros are, I guess. Or, you know, set up an augmented matrix, solve the system, see if you get non-trivial solutions or not. For the next one, oh, you know what? We've got more vectors here, more vectors than entries in each. That was theorem 8. More vectors than entries in each, so linearly dependent. Okay. I see another way to answer this one. Should we do that? Should I tell you another way? Sure, why not? Let's answer this another way. Or I notice that 1, 1 is a linear combination of the others. And that one would be theorem 7. Okay, so could be more than one shortcut that applies. And of course, there's also the original way of setting up an augmented matrix and solving, checking if there's non-trivial solutions. Part C, there's 2 vectors, so we could potentially ask ourselves if one of them is a multiple of the other. Maybe it's a little bit unclear. You know, could I multiply this first vector by something in order to get the second vector? Do a little scratch work if you need to. But here we do have 2 vectors, and one is a multiple of the other. I think in this case, since it might not be immediately clear, I'm going to demonstrate the multiple. I'm going to say that 1, -2 is equal to -2 times the other vector. You know, because maybe you see that immediately, but maybe you don't. So let's just say it. And what's the conclusion, right? Don't forget to write the conclusion. And make sure you write the correct conclusion. What do we conclude from 2 vectors and one is a multiple of the other? That means that the set is linearly dependent. One thing to be careful of is sometimes I see students, sometimes they have all the correct work, they have all the correct justification, everything looks beautiful, and then at the very end, they write the wrong answer. So double check the final answer that you're writing. You know, in those situations, I want to give partial credit, so I give partial credit where I can, but it's better if you have the right answer. All right, part D. So maybe we have a couple of options for part D. So I guess this is 3 vectors. So we can't use the thing about only having 2 vectors. We can't use theorem 8 because we don't have more vectors than entries. The number of vectors and the number of entries is equal. So we can't use theorem 8. We could try to use theorem 7. Is one of these a linear combination of the others? I would say it's hard to tell. I would take some work in order to tell if one of these is a linear combination of the others. I don't see a linear combination jumping out at me. Thinking about putting like weights in front of 2 of them and trying to get it to equal to third. It doesn't look clear. So I think what I'm going to do for this one is I'm going to solve like we did in example 1 and example 2 at the start of the section. I don't think that the shortcuts are very quickly applying to this situation. So let's set up an augmented matrix and solve, and that is always going to work. It's always going to get us an answer. So augmented matrix would have zeros for the right-hand side, and we start working on row reduction. I guess looking at these examples, it looks like I didn't actually give you any examples that use Theorem 9. So maybe you'll see some of those when you do other practice problems or when you do homework. Remember, Theorem 9 said that if you see the zero vector included, then you can immediately reach a conclusion. But anyway, let's just focus on this. Let's do some row reduction. I decided I'm going to do two steps at the same time. I said it's okay to do that as long as you are careful. I'm going to add 5R2 to R1. Can you see why I'm doing that? And also I'm going to multiply row 3 by 1/2. Hopefully you can see why I'm doing that. So that is going to make the first row look like 0, -2, 5, 0. Second row stays the same. Third row gets a little simpler. Next, I decided I'm going to add 2R3 to R2. And at the same time, I'm going to add 2R3 to R1. Yeah, that's going to get us some zeros in some spots. Again, you could do some of these steps in different orders. You might have a different set of steps that gets you to the same place, but I got 0, 0, 13, 0. I got -1, 0, 9, 0. And I got 0, 1, 4. That third row is staying the same. Next thing that I saw was that 13 there. Look at all of row 1, 0, 0, 13, 0. I want to just multiply row 1 by 1/13. If I multiply row 1 by 1/13, that's going to become a 1. I also want to interchange rows. Hopefully it's okay with everybody if we do that at the same time. So I'm going to multiply row 1 by 1/13 and then interchange rows. So I'm going to put this row on top. I'm going to put this row in the middle. It makes sense for this to go in the middle. And the row 1 that got multiplied by 1/13 is going on the bottom. Get that nice triangular form. Okay, so this is in row echelon form. It's not in reduced row echelon form, but it's in row echelon form. Do we need to keep going? Check this out. Remember we said that a homogeneous system has non-trivial solutions if and only if there is at least one free variable when solving. So I am going to say that you could stop here. You could stop here. Ax equals 0 has no free variables. How do I know that? How do I know there's no free variables? It's because we have row reduced enough to see that there are 3 pivots. Pivot, pivot, pivot. We're going to get, if we keep going, we're going to get an answer, just, a unique answer. Not like a solution set with a free variable. So there's no free variables, so there is only the trivial solution. I'm going to show this to you anyway. I'm saying you could stop here, but I'm going to show you anyway that if you continued with row reduction, it would row reduce to this. This would be in reduced row echelon form. And this would tell us that C1 is 0, C2 is 0, C3 is 0. Only getting the trivial solution. So as soon as you can tell that there is only going to be the trivial solution, you could stop. All right. Or on the other hand, as soon as you can tell that there are going to be free variables, if you did this and you saw a free variable, you could stop there and you could reach your conclusion, right? So my conclusion is that part D, this problem, is linearly independent. Independent because we are only getting the trivial solution. So that's the hardest one, right? We didn't have any quick shortcuts to do it for us. We had to do it the old-fashioned way and solve the system. Okay, so we'll be wrapping up this section in just a moment. I'm going to leave this on here in case anyone is still copying that. Okay, so that is the end of our lesson on linear independence. We started by having the definition of linear independent and linearly dependent. And then we solved a couple of problems sort of manually by solving a system to figure out yes or no. And then we had a bunch of theorems or properties or shortcuts that help us to quickly answer some of these. But as you saw in that last problem, sometimes you just don't have a shortcut, and sometimes you have to solve the augmented matrix and find the solution or find the answer that way. So that's all about linear independence. Now, at this point in the course, you could be wondering, why do we care if a set is linearly independent? Hopefully you've seen that it has some connection to whether a system has a solution or not. So that's one reason you might care. But basically, as the course goes on, we might have other theorems or other facts that have to do with other concepts we haven't even gotten to yet. But then they might use this phrase, linearly independent. Blank, 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 only if this thing is linearly independent. So that's why we want you to understand this concept. It's going to be used later for some other things. So where we're at right now, I've been kind of following along the order of topics from the recommended textbook. And the next topic we have is linear transformations. Now, in this textbook, everything we've been doing so far is Chapter 1. Chapter 1 is really supposed to be introducing us to a lot of different topics in linear algebra. Linear combinations, span, solving systems with no solution, solving systems with infinitely many solutions, linearly independent sets of vectors. Linear transformations, which are the next section, are a very important part of linear algebra. And linear transformations are something that we could really discuss for the rest of the semester. I think they'll keep coming up again and again. So don't miss that one. It's going to be a good one. All right, so thanks everybody for watching, and I'll see you next time for linear transformations.